Welcome. In this video, we're going to discuss the bug problem. So we have a hexagon below, and a bug starts at vertex A. So we'll put the bug right there at vertex A. And each minute, it travels to an adjacent vertex. So it makes one move in a minute, and then from vertex B, it could go to A or to C. So we'll stick it back at A. Now, there's a spider web on vertex D. So once the bug gets to the spider web, it stays there. It's stuck. So there's no more moving after that. So A sub n will represent the number of different ways the bug can travel from vertex A to D after n minutes, or you could think of the n minutes as moves. So let's calculate the first few examples to get started. So if the bug has one move, it can go from A to B, or it could go from A to F, but it just can't get to the web down here. So there are no ways to get to the web. So A sub 1 is 0. Now if the bug has two moves, it could go like 1, 2, or it could go 1, 2, or it could even go like 1, 2, but it's just not going to get to the web again. So again, A sub 2 is 0. Now for A sub 3, at least something sort of interesting happens here. We can go 1, 2, 3. Or you could go 1, 2, 3. So there are two different ways that you can get to the web. Now with 4 moves, the bug has an even number of moves and can only ever make it to A, E, or C with an even number of moves. Can never make it to the web with exactly an even number of moves. So that one is also 0. Now once we hit A sub 5, it already gets a little bit challenging to calculate. The bug could do 1, 2, 3, 4, 5, or the bug could do 1, 2, 3, 4, 5. It seems like there's a number of different ways that this could occur. And usually when the counting gets too complicated, I try to think recursively from there on. Okay, so we're going to try to build a recurrence relation for A sub n. And to help us along, we're also going to define B sub n to be the number of different ways the bug can start at B and get to the web, and so on. C sub n will be the number of different ways that we can start at C, and all the way down to F will be the number of different ways we can start at F and get to the web. Let's start by thinking of the bug's first move. The bug's first move is to F or B. So this means that A sub n is equal to B sub n minus 1. We move to B with one less move, or we can move to F with one less move. Now, there's something else to consider. There's symmetry between F and B. If we think of the line of symmetry that goes through A, it perfectly divides our hexagon into half. And now we can consider the starting move to B being the same as the starting move to F. So returning to our equation, the B sequence is the same as the F sequence, so we can write 2 times Bn minus 1. And let's write that that's by vertical symmetry. So we have a start. A sub n is equal to twice B sub n minus 1. And what we need is a formula that just has A sub n's or A sub n minus 1's or whatever, but no more B's. So let's try to think about, well, what happens if we move the bug over to B and we think about all the options that the bug has from B and go from there. So from B, the bug can either go to A or C. So this means that B sub n minus 1 is equal to A sub n minus 2 plus c sub n minus 2. So let's remember, A means that the bug is starting from vertex A, and the n minus 2 means that it has n minus 2 moves left. And C, we're starting from C and we have n minus 2 moves left. So we were at B, we used one move to either go to A or to go to C. Let's focus on the C sequence. Something interesting happens there. When the bug uses its second move to go to C, most of the time it can't go to the web directly. Most of the time it must go back to B. So as long as the bug has to make more than 3 moves, the bug actually has to go directly back to B. So in our equation below, we can write that down as B sub n minus 1 is equal to A sub n minus 2 plus B sub n minus 3, and there's a condition on this. This is for n values that are strictly bigger than 3. Now we have two equations that we can put together. A is twice bn minus 1, and we solve below for another way to write b sub n minus 1. Let's call this equation 1 and this one equation 2, and let's put them together. So a sub n is equal to twice b sub n minus 1, which is equal to a sub n minus 2 plus b sub n minus 3. Now let's expand out this equation to get 2a sub n minus 2 plus 2b sub n minus 3. Remember, our goal was to write this all in terms of A. Now we've discovered that twice the B sequence gives us the next term in the A sequence. So we can use equation 1 all over again to get the result that we're looking for. So this is equal to 2a sub n minus 2 plus a sub n minus 2. That's by equation 1. Now if we just clean this up a little bit, we can add those terms together. So we have 3a sub n minus 2. This gives us a nice form for our recurrence relation. Now, in order to state our final recurrence relation, we do want to have some initial conditions. And let's remember that this equality right here, we're not allowed to plug in n's that are smaller than 3. We can plug in 3, we can plug in 4, that's fine. But because of this condition, along our travels, we had this condition that our n had to be bigger than 3. So we can go ahead and give an initial condition for a sub 3. Let's remember above, we did calculate that as 2. And to properly define this sequence and make a proper recurrence relation, we do need to give 2 initial conditions, because we're looking 2 steps back. If we just left it at a sub 3 as 2, we would only define the odd terms in this sequence. So we do need to also define that a sub 2 is equal to 0. This successfully defines our recurrence relation. So the recurrence relation says we look 2 terms back and we multiply by 3. Let's go back above, scroll back up to where we were, and try that out. We were saying that, oh, for a sub 5, it was a little bit difficult to calculate, but now if we just look 2 steps back, we can see that, okay, that number should be 2 multiplied by 3, so that should be 6. And if we kept going, a sub 6, well, that should be 0, because it's 2 steps back, giving us the 0, and multiplying by 3 is 0 as well. Then if we wanted to do one more, we would get a sub 7, and you would do 6 times 3, giving you 18. And at this point, we can already see that it would be a really big headache if we had to count 7 different moves with the bug and count all the different ways of 1, 2, 3, 4, 5, 6, 7 that the bug could arrive at the web. There would be 18 in total of those different ways. So thanks so much for listening, and we'll see you on the next one.